Let's distinguish linear from angular velocity in this video. Welcome to Mathematics of Engineering. What is velocity? Velocity is what we know as speed, only that this has direction as it is a vector, while speed is a scalar. Anyhow, velocity is defined as the change in distance with respect to time. Take for example a traveling car. If the distance it travels in 1 second is 5 meters, we can write velocity as the distance upon time, or 5 meters per second. In short, velocity can be mathematically written as s over t. Delving deeper into the types of velocity, we have linear velocity, and this is how fast an object travels at a specific time. In a circular path, linear velocity is the arc length upon time. Since arc length is s, we say v is s all over t. Angular velocity, on the other hand, measures how fast an object rotates. Thus, omega is computed from arc measure all over time, that is theta all over t, and its standard unit is radians per second. Now let's check the relationship of v and omega. An equation we used previously in relating two parameters was arc length as equal to radius times angular measure. This is taken as the distance level. By differentiation, velocity is then generated as v as equal to r times omega. Check the first application, stated as Jack climbs on a horse that is 12 feet from the center of a merry-go-round. The merry-go-round makes 3 1/4 rotations per minute. Determine Jack's angular velocity in radians per second. What is Jack's linear velocity? To determine the angular velocity, there is a given parameter omega at 3 1/4 rotations per minute. Rotations is the same as revolutions for this concept. So, to keep a standard unit of omega, we multiply the conversion factor of 2 pi is to 1 circle or 1 revolution to cancel out revolutions. Furthermore, as the instruction requires radians per second, convert minutes into seconds and cancel out minutes. Omega is then 3.25 times 2 pi upon 60, which is computed as 13 over 120 pi radians per second, or that is 0.34 radians per second. The next requirement is linear velocity. So with omega already transformed, we use v as equal to r omega, where the radius was given as 12 feet. This is multiplied by the transformed omega of 13 over 120 pi to have 13 over 10 pi, or 4.08 feet per second. For the next example, we determine the linear velocity of a point rotating at an angular velocity of 12 pi radians per second at a distance of 12 centimeters from the center of a rotating path. When looking for linear velocity, radius is a necessary parameter, so we use v as equal to r omega. By directly substituting the given values, we create 12 cm times 12 pi in radians per second. V is then solved as 144 pi, or 452.39 centimeters per second. The third example includes bicycle tires which have a diameter of 60 cm. The tires turn at a rate of 50 revolutions per minute, and we are to determine the velocity in kilometers per hour. From the unit of kilometers per hour, we are looking for linear velocity, so we are to use v as equal to r omega. With the diameter given as 60 cm, radius is then 30 cm. This we need to convert, as instruction states that velocity should be in kilometers per hour. Convert 30 cm into meters and then into kilometers, having r as 3 over 10,000 kilometers. Omega is also given as 50 revolutions per minute, but we need to convert this entity by first multiplying 2 pi radians is to 1 revolution, so we can cancel out revolutions. And then we again multiply 60 minutes is to 1 hour to convert minutes into hours. So omega is then 6,000 pi radians per hour. Finally, the linear velocity is then 3 over 10,000 km times 6,000 pi radians per hour, which is then solved as 9/5 pi, or that is 5.65 kilometers per hour.